here is that there will be a short circuit path from this point to the ground. So all of the current and power will be returning back to the system, and there will be no power transferring to the infinite bus. So that's why the P2 max is completely zero. Network after fault, the assumption is that when the fault is clear, both lines are assumed to be intact. That means again this network remains the same as the before fault network, and you can calculate the X equivalent after fault. That will be exactly equal to the X equivalent before fault. Okay, that will be the case. And if we put this value here, then we will get the P3 max. That means this P3 max will be equal to P1 max. So the maximum power transfer in the after fault scenario will be equal to the maximum power transfer to the infinite bus in the during fault, in the before fault scenario. This will be equal. And then we can draw this thing, and we can understand the trajectory of the rotor angle. This curve represents the before fault and the after fault power angle curve, and the during fault power angle curve actually represents this horizontal line where the P is right. So this is our during fault curve. So our initial operating point will be this A. Then if there is any fault, then there will be a jump from point A to B. Why? Because this is our during fault curve, right? So now the system is in the during fault region. Here in point B, the P is higher than Pm, right? So there will be acceleration. So omega will increase as well as the delta will increase. That means the journey will be in the right hand side and following this horizontal line, and it will come at point C. That is the fault clearing point. Now let's say at point C the fault is now cleared out. So what will happen? There will be another jump from point C to point E. Yeah, on this curve. Because now we will be in the after fault region. And after fault curve is also same as the before fault curve. So that means it is here. So in the acceleration phase we have covered some area, that is this area, that is A1. Now at point E, the P is here the Pm was higher. Okay. Here the P is higher than Pm. So what will happen? The omega will reduce, right? Start to reduce because there will be now deceleration. But in the acceleration phase, let's say the omega has gained some higher value. Okay, that's why whenever it starts to reduce, it is still higher than the synchronous. That means the difference between omega minus omega naught will still be positive. So our delta will still increase, right? That means now the journey will be across this curvature and to the right, and it will come up to point F, so that this decelerating energy can be equal to this accelerating energy, right? And at point F, omega will be equal to omega naught. But again here the P is higher than Pm, so deceleration continues. That means now the omega value will actually fall under this omega naught, and this difference will be negative, right? So delta will now decrease. That's why from this point F, now the journey will be in the backward direction to F, to E, okay, and then E to this A, following this curve. Now in this journey there is stored decelerating energy that should be given back in the accelerating side. So it will come here, maybe it will come below this 0 point, so that this area can be equal to that area. Okay. So let's say this point is point K. So now in the next cycle, it will again go to the F, then again it will come to the K. And if we do not consider any damping, then this will be the case. There will be sustained oscillation between these two fixed points, F and K. But if we incorporate damping effect, then at each cycle this oscillation will decrease, right? Maybe in the next half cycle it will come up to this point rather than going to the F, and then in the next half cycle it will come maybe here, not to K. Then in the next half cycle this difference will reduce gradually, and finally what will be the final equilibrium point? K. Again we will get this final equilibrium point, right? That is the case. Then we actually derive the critical clearing angle delta C. What is that delta? This is the limiting case where actually all of our decelerating area has been used. That is, this area is equal to that area. Okay. We can delay the fault clearing time further from this point. Because if you delay further, then this area will be higher than that area. And at that time, the system will be unstable. So that's why this is the critical clearing angle delta C. So we have actually found this expression in the last class, and we applied this to get the value for delta C. Then we had also the TC expression, that is the critical clearing time. And using these two equations, actually we solved this example A. Okay. And now in today's class we will begin from this part B. And here the same system with the same data and similar type of fault, the three-phase voltage fault, but the location of the fault is now changed. Now the fault occurs at the middle of one of the lines. That means here we have two lines. So now the fault occurs at the middle of, let's say, this line. Okay. And the assumption is that when the fault is cleared, the faulted line, that means these lines will be isolated completely from the system. And now we have to determine the critical clearing angle, that is the delta C, right? And remember, we can calculate the TC analytically here for this case. Can you remember? In the last class, we said that for this case, whenever the fault is away from the sending end, we actually can't get any analytical solution for TC. So that's why only we need to calculate the delta C. So how can we proceed? So this is this case, the three-phase fault away from the sending end. And for this case, we actually normally get three types of power angle curve. Why? Because we had three networks. The first one is before fault, and this is exactly same as the previous case. We have all of our reactances and all other components are present. So we can calculate X equivalent before fault. If we put it here, then we will get the P1 max. Then the network during fault. So here the fault is here. So there will be a short circuit path from this point to the ground, and the total reactance will be divided into two. So half will be in this side and half will be here, right? X1 divided by 2. So that is here. Now we can add these two, X3 plus X3 dash, then we will get this thing. Now these and these three are forming a Y network, right? We can convert it into delta network like this. Then the equivalent reactance between these two voltage sources will be simply this, right? Then using the Y to delta proportion formula, we can apply this and we can find it. Then we can put it here to find the P max. That is the maximum power transfer during fault scenario. Then the third network is the after fault network, and here the assumption is that when the fault is clear, the faulted line is removed from the system by opening the circuit breakers. That means there is no second line which was affected by the fault. So now this is our new diagram for after fault scenario. So here the equivalent reactance will be the addition of these three reactances. So we will get this X equivalent after fault. Then once we know this value, we can find the P3 max, right? Now you will see that this P3 max, P2 max and P1 max, these three actually are different. Okay? And if you put these values in a single curve, then you will see that this is your P1 max, this will be your P2 max, and this will be the P3 max. Okay? And the maximum value will occur at pi by 2. So you can complete the drawing from 0 to pi, then you will get the curve A for before fault scenario, curve B for during fault scenario, and curve C for the after fault scenario. Okay. Then what will happen? Let's try to understand the trajectory of the rotor angle. Let's say this is the point A, initial operating point, and obviously this should be on the curve of A, right? Because this curve A is the default fault curve. So it is here. Then if there is any fault, this point A will jump to the point B. Why? Because this point B lies on the during fault curve. Okay, now we are in the during fault region. Then point P, again the P is lower than Pm here. There will be acceleration, and due to acceleration, omega will increase as well as the delta will increase. Okay, so the journey will be the right side towards curvature, and it will come at point C. This is the fault clearing point, and whenever the fault will be removed, this point will jump to the point E. Why? Because this point lies on the after fault curve. Okay, and in the acceleration phase, we have covered the area A, B, C, D. This area, that is our accelerating area. Now at point E, the P is higher than Pm. So now there will be deceleration. Means the omega will reduce now. Okay. But the previously in the acceleration phase, the omega is now still a higher value than the omega naught. So still the omega minus omega naught difference will be positive, and the delta will increase, right? That means that from E there will be a journey to the right side up to point F, such that this DEFG, this decelerating area, can be equal to the accelerating area ABC. And at point F, again we will have omega is equal to omega naught. But at F, P is still higher than Pm, so the deceleration continues. That means now the omega value will fall under this omega naught value, and this difference would be now negative. So our delta will now decrease. Decrease means from F, the journey will be in the left side now. Okay. So let me clear what the red line here. From here, now the journey will be in the backward direction following this curve C. Because now we are in the after fault scenario. So it will come up to this point. Let's say this point is generated by P's. That means we have covered, we have restored this decelerating energy. Then it will cross this point H, and it will come up to here, here, so that this area can be equal to that area. Okay. Let's say this point is K. Now, if we do not incorporate any damping, then again from K it will go up to F. Then from F it will come again to K. So the system will be marginally stable. There will be sustained oscillation, and the oscillation will be in between these two fixed points, from F to K, and again from K to F, like this. But if we consider the damping effect, then what will happen? After each cycle, the oscillation will decay, and finally, what will be our final equilibrium point? It will be H, right? This point will be our final equilibrium point. So that means we are getting a new equilibrium, because this is delta H, right? But previously our initial operating point was delta naught, right? But now we are getting a new equilibrium point, delta H. Yeah, in this way. Now for this case also we can solve for the critical clearing angle. How? We have to take this case where, let's say, this is our fault clearing point. It is such that all of our accelerating energy is here equal to the decelerating energy here, but there is no available decelerating energy left here in this side. That means we have used all the area in the decelerating phase. So that means if we move further from this point to the right, that means if we allow further delaying in the fault clearing, then this area will be higher than that area, and the system will go into the unstable state. That will be the case. So this is our limiting case. That is the critical clearing angle, and we actually derive this expression. It will be simply this. Okay. But to apply this equation, we have to know the delta max, Pm, P3 max, P2 max. This way. Okay. That's why. To solve this thing, first we have to calculate the P1 max, P2 max, P3 max, delta naught, Pm, as well as delta max. Once we know all of these values, then we can write the expression of delta C. Okay. Now let's try to find all of these parameters. So the power angle curve before the occurrence of the fault, that is the before fault, is the same as in case A, right? In the case A, the before fault network was the same, right? We are actually considering the same network, single machine infinite bus system. And the data for case A and B both are same. Okay? So we will use the same thing. So these values have been taken directly from the previous example, example 11.5a. So in that example, we got that the P1 max, that is the P max before fault, it is 1.8. Okay, and the delta naught, it is 26.387. These two values are directly taken from the previous example. Good. Here, solve it. ক্লাসও করো না কেউ করো মানে কিসের জন্য আমি ক্লাস করতে কি কাজে করে সেখানে দরজা লাগাই দিয়েছি এই দরজা লাগাই দাও this was the part A. Okay, here we calculated this delta naught as well as the P max before fault. That was 1.8. So look, we are taking this values directly from the part A. Okay, 1.8. This is before fault scenario. Now the fault occurs at point F at the middle of one line, which results in the circuit showing the following figure. So if the fault is here, what figure will look like this. Okay. Now how we will calculate the equivalent reactance? First let's add these two, then we will get this, then these three will form a Y network, we will convert it into delta. Then only this reactance will be the equivalent reactance, right? That means this reactance will lie in between here. This is our x2 here, okay? And what will be this x2? It will be, let's say this is 0.5, this is 0.3, and this is 0.15. So in the numerator side, we have to take two reactants at a time and we have to multiply and plus the rest of them. So 0.5 multiplied by 0.3 plus 0.5 multiplied by 0.15 plus 0.15 multiplied by 0.3. Okay. And in the denominator, we have to take the opposite reactants, that is 0.15. For this is 0.15. Okay. So this is our x equivalent during fault. Now you can just put this value here, 1.8 per unit, you will get the P2 max, that is 0.65. Then the network after fault. The assumption is that the faulted line will be isolated. So there is no faulted line, no second line. So what will be the x equivalent after fault? The addition of this, and this. It will be 0.8. So our P3 max will be 1.4625. Look, this is the P3 max, this is P2 max, and this is P1 max. These three are different, right? Now we can plot these three sinusoidal curve. This is for the P1 max, that is, this is the before fault curve. This is with the P2 max, that will give us the during fault curve. This is the after fault curve, right? Now we have to calculate the critical clearing angle. What will be that angle? That angle will be this angle. So that all of the decelerating area can be used. So there will be no available decelerating area, right? So obviously this red line area is equal to the green line area, and this is at the highest limit F. Okay. And we have to calculate For that, this is the formula. Okay. We have calculated PM. PM was calculated in part A. We calculated it. How? In this point, look, you know the delta naught, right? So it will be PM and P1 max sin delta naught, right? We calculated this, then also we calculated this. Okay. Then we can know this PM. Okay. Then we calculated P3 max, P2 max. Also we know the delta naught, but we haven't calculated the delta max. How can we know this value? Look, it is shown here. How? This point A. And there is another point which is actually symmetrical to this point. This point A. This A point is another point. Look, it is not another point. F is in the second point. So this point A is, and this point F, these two are actually the symmetrical points. So if this is delta H, so the summation of delta H and delta max will be pi or 180 degree. Okay. So what will be the value of delta H here? So it will be, look, for point H, you can write PM is equal to, this is the after forecast, right? So it is P3 max sin delta H, right? So delta H will be sin inverse PM over P3 max. Okay. Then this delta max will be simply 180 degree minus delta H. Okay. Look, delta max 180 degree minus sin inverse PM divided by P3 max. This is the PM, this is the P3 max. All the values are known. We just calculate, we get this thing. Okay. Then the cos inverse of this will give us 98.834 degree. So this is the delta C. So the delta C is the 98.834. That was asked in the question. So we have calculated it. So any question up to now? Now these are the time domain analysis. Delta versus time. This is delta versus time. So this is delta versus time, right? And these three curves are for three different fault clearing time. Here the fault clearing time is 0.1 second. Here it is 0.2. Here it is 0.4. So what is the difference between this curve and this curve? Can you see? The fault clearing time has been increased. What is the difference? Obviously, these figures are without gambit. Okay. That means we are getting the marginally stable case. So it is swinging between two fixed curves, right? So it is not purely stable. But what is the difference between these two curves? So the delta max, right? Here the delta max is below 60, but here the delta max is close to 70, right? Why? Because if the fault clearing time is higher, that means we are allowing more time. So that C point then will shift in the right side, right? So this will be the new C. So at that time the accelerating energy A1 will increase, and to completely dissipate that energy in that side, this F will also move to the right side. Okay? And that means this delta max will increase. That's why for this increased amount of fault clearing time, we are getting delta max higher than delta max. And whenever it is 0.41, look, after 5 seconds, it is increasing. It is going to the unstable state. That means this is beyond our critical fault clearing time. For this example, we only calculated the delta C, and we said that there is the analytical solution for DC. So how can we change that value? We will just do the trial and error method. Okay, so we will run the simulation, then we will increase this fault clearing time. Let's say we will take it 0.3 second. Then we will see that okay, the system is still stable. Then we will increase it to 0.35. Then we will see that okay, the system is stable. Then whenever we will take 0.4, then we will see that the system is now unstable. So then we can decide that this 0.4 is the critical clearing time DC for this case. That is the case. Okay. Now this is the simulation for 2 seconds without damping for this case. So this horizontal line with the TM line, this green circle will give us the rotor angle trajectory, and this curve is the after fault curve, and this is here the initial operating point, here the before fault curve. Okay, this is the before fault curve, and this portion is the during fault. That means there was a sinusoidal curve like this. Okay, this is the during fault. So this is the initial operating point. So whenever there will be any fault, this point A will jump to the point B here, right? Then it will move across this curvature and it will come up to point C. Let's say this is the fault clearing point. After this point, there will be a jump to the point E on this after fault curve. And in the acceleration phase, we have covered the ABCD area, right? This area. Now, this E will move to this side and it will come up to point A. So that this area, DEFG can be equal to the area ABCD. Then as there is no damping, from this point F, it will go backward and it will cross this TM line and it will come up to this point K. Then in the next cycle, again this point will go to exactly at point F, then again at K. So this oscillation will be in between this F and K. Okay, so this is the sustained oscillation because there is no damping. Okay, so we will see this thing here. The fault has been given at t equals to 0.1 second. That's why before 0.1 second there is no fault. So this is the time information. So as there is no fault, the point is here. At 0.1 second there will be fault. This point will jump from here to here. Now we are during fault distance, and we have assumed that the fault is clear at 0.26 second. So whenever time t goes to 0.26, then we will see another jump from this to the power angle curve of the after fault regime. Okay. And now it is coming to here, point F. Then from there it will move backward. And it will follow this curve, it will come up to this point A. Okay. Then in the next cycle, it will go exactly at point A. There is no decay, right? And again it will come up to K. Then again it will go to the F, right? So as this simulation is for 2 seconds, if you increase the simulation time up to 5 seconds or 10 seconds, you will see this thing in a repeated manner, right? So you will see this phenomena again and again. Now this is the case for with damping. So if there is any damping, what will happen? After some moment we will get an equilibrium point, right? And will it be a new equilibrium or will it be the old one? It will be the new one, right? So this is the delta naught. Okay, and this is the delta X. Okay. Also this is delta 1, delta naught, this is delta X. This is for 0.15 second for clearing time, and this is for 0.25 seconds. Okay. And this is for 0.55 seconds. So here there is one important observation, that is previously at 0.41 second the system went into the unstable state. But here, as we have added the damping, that's why the critical clearing time will increase, right? Maybe for this case, let's say this is 0.6. That's why below this value we are seeing that the system is still stable, right? And here also this is, let's say, delta naught, and the final value is delta X. Now this simulation for weak damping, this is the PM line. Again, this curve is the after fault curve. There is another curve here during fault, and this initial operating point here. We have the before fault curve. Okay. So here this is the green circle at the initial operating point. At time t equals to 0.1 second, it will jump to this point, and it will follow this curve, and it will come here point C. And at point t equals to 0.26 second, the fault will be cleared out, and it will jump again to from here to here point E, right? Then it will move across this. This is the point F. Then it will move backward, and it will come at point K. Then in the next cycle, as there is damping, so it will not reach to F, rather it will come here, right? Then in the next half cycle it will come here. Then in the next half cycle it will come here. So like this way, after some moment, it will reach to a new equilibrium. What is that point? This point, the intersection of this curve and this beam, right? Let's say this is our point X. Okay, so that is actually our delta X. Okay. Now let's run the simulation. So at time t equals to 0.1 second, the fault will be there. So now the fault will sustain up to 0.26 second. That is our fault clearing time. And at 0.26 second, there will be jump from here to there. Then it will follow this curve. Then it will go to there. It's coming there. Then it is moving backward, right? It is coming to that point K. But in the next cycle, it will not reach to that point F. Okay, look. It is reaching up to this, and from there it is again moving back. Okay. Then here again it is coming up to this point. Then again it is moving forward. Okay. And this simulation is for 2 seconds. If you increase the simulation time, let's say for 5 or 10 seconds, then we will see that after 5 or 10 seconds, the point, the green circle will be here. That is our new. This is the good template. So, any question up to now? So, we have actually covered the 11.3, 11.5 part B. Now, there is another small portion with this question. That is the second part. It is called the breaker reclosed. What does it actually mean? Let's think about this stuff. So now the location of the fault is same as before. It is actually at the middle of one of the transmission lines, and this is the after fault network, right? Because the assumption is that when the fault is clear, the faulted line will be isolated from the system. So there is no faulted line here. Okay. But we had this line before, right? We had this line. Due to fault, the circuit breakers in this side and in this side actually operated, and these two circuit breakers were open. That's why this line is not disconnected from the system. That is the case, right? But before the fault, these circuit breakers were closed, and this line was there, right? So you can actually operate the system without this line. That's okay. But this line you have bought it with money, right? So as a power system operator, you will think that I should utilize this wire again. So you can't disconnect it forever, right? So what will be the point of that line there, right? So somehow again you have to connect this line to the system. So how you will connect, and when you will connect, and what is the benefit? Okay. The benefit is that if this line is missing, let's say that xt dash is 0.3, xt is 0.2, and x1 is 0.2 also. If this line is absent, what what is the equivalent reactance here? Simply the addition of this thing. Equal to 0.7, right? So you will get the Pmax using this formula. It's 0.7, right? But if you can connect it here, let's say, then it has also 0.2 per unit reactance. Now the parallel combination of these two will give you 0.1 plus this. It will be 0.6. Now the new Pmax will be, the numerator will be same, but with the new denominator there will be 0.6. So this value will be higher than the previous one. That means if we can connect this line to the system, then we will be able to transfer more power from the sending end to the receiving end, right? That is our obvious target. That's why as a power system operator, always we need to connect this line again. Okay? And whenever we will connect this line again, the circuit breaker will again be closed. That's why it is called the circuit breaker reclosure. Okay? So this phenomenon is called the circuit breaker reclosure. Okay? Because here the fault is temporary fault. So after some moment there will be no fault. The fault will be vanished, right? So at that time again you can bring back this line to the system. There will be no harm, right? So that's why this is the circuit breaker reclosure. Now tell me, after reclosing, this is the picture of the network, right? This is same as which case? Before fault case, right? That means the X equivalent after reclosing will be exactly equal to the X equivalent before fault, right? If this is true, then the Pmax after reclosing will be equal to the Pmax before fault, right? That means we drew the before fault line previously, right? That can be treated as the after reclosing power angle curve. So this same power angle curve will be now the before fault as well as the after reclosing power angle curve. Okay. Now let's with this concept let's move forward. Breaker reclosed. So our X equivalent reclosed will be equal to the X equivalent before fault, and the circuit diagram will be same as the before fault. Okay. This line again is again back to our system. So the P4 max, that is the case 4 after reclosing, will be equal to the P1 max. That is the case 1 before fault. Now what will be the rotor trajectory? This is the initial operating point. Now this curve is the before fault plus after reclosing. This curve is after fault and this curve is during fault. So this is the initial operating point on the before fault curve. If there is any fault, it will come to B, that is on the during fault. Then the journey will be the right side up to C. C is the fault clearing point. Then from here we will go where? Point E, that is the after fault. Now the accelerating area A1 is ABCD. This is the area A1, ABCD. Now we will come up to point F. At point F, this is the delta RCM, the reclosing angle. So at point F, our breaker will be reclosed. Okay. That means now there will be another jump from this point F to the point I, right? Then again this point will move right, because still we haven't got this same area, right? Because again in the decelerating side the area should be equal to the area A1. That's why we have come up to point J, so that this area DEFG plus this area HIJ can be equal to the area A1. Okay. So that's why we have come up to point J. Then from J, the journey will be in the backward side. Now we will follow this curve, right? This is the after reclosing curve. Then we will come up to this point A. So there is a huge decelerating energy stored. Then to give that back the system, we will come up here. So that area can be equal to that area. So again that point will be the point K. Then this point K to again the movement will be up to point J if there is no damping, right? Then from J to K. So again, if there is no damping, there will be a sustained oscillation between this point to this point. Okay. But again, if we consider the damping, what will happen? This oscillation will decay, and what will be the final equilibrium point? It will be the A. Look, this is the initial operating point. So in this case, our final equilibrium point will be the old one of the previous one, right? But in that case, it was the new one. So now the final point is the delta max, and at the point where the delta was closed, that is the delta RCL, and this is the non-critical clearing case. That means we have still some available area left in the decelerating phase. Okay. So what will be the critical clearing phase? That will be the limiting case. Okay. Let's say we allowed more time, okay, to clear the fault. That's why this C is now shifted in the right, such that to mitigate this area, all of the available insulating area has been taken. Look, now this area A1 is equal to this area A2. That is the summation of area TEG plus T size. So there is no more area left here. So this is the limiting case. That's why this angle is called the critical clearing angle for this case. Okay. Now how can we express this magnetically? We have to apply the formula. Look, the area A1, this area, ABCD. This is under between these two curves. This curve, PM, and this curve, right? This is the during fault. Means this is actually the P2 max sin delta, right? So look, PM minus P2 max sin delta, and the equation will be from delta naught to delta C. Okay. This is area A1. Area A2, area DEFG. That means that this area DEFG is under between this curve and this curve. This is PM, and this is actually the P3 max. After form of curve, that's why P3 max sin delta. So P3 max sin delta minus PM, and the equation will be from delta C to delta RC. Okay. Plus this area is IZ. It is the area under between this curve and this curve. This is PM, and this is the before fault curve. That means this is actually P1 max sin delta, right? So this is P1 max sin delta minus PM, and the equation will be from delta RCL to delta max. Okay. Now you can easily equate these two, and you can find the expression for delta C, right? So that will be your task to find the expression for delta C, and then you have to put all the values, because we know what are the values rather than this value. Okay. Only this is our unknown, but we know delta naught, we know the PM, P2 max, P3 max, T1 max, PM, and also this delta RC will be given in the question paper. And how can you find the delta max? So once we know the delta naught, now look, this delta max and this point, these two are the symmetrical points. That's why this delta case will be simply 180 degree minus delta. Okay, this will be the delta max. So if you put all the values, then you will be able to find the delta C for this case. So that hasn't been shown here, but you can do it by yourself. Okay. And now this is the time domain analysis, delta versus time, and this is with damping. So with damping, the oscillation will decay, and what will be the final equilibrium? It is delta naught. It will be also delta naught. Why? Because this is the break of the closed phase. Here we are getting the same equilibrium point, right? Also here this is delta naught. This will be the delta. Okay. Obviously this is 0.15 and this is 0.25. That's why there is the delta max is higher. It is 50. It is 70. And what will be the simulation? This is the before fault curve plus the after the closing curve, the same curve. This curve is actually the during fault, and this curve is after fault. Okay. And this is the PM line. This horizontal line is the PM line. This is the for point A. So when there is any fault, it will jump to point B and it will follow the given fault curve. It will come up to point C. This is the fault clearing point. So whenever the fault will be cleared out, it will jump to point E on the after fault curve. Then it will come here at point F. This is our delta RCL. When the circuit breaker will be reclosed again, okay, then it will go to the before fault. That is the after reclosing curve as well. Then it will come to here. Then again it will move backward and it will come here. Then if we add damping, then in the next cycle it will come here. Then again it will come here. Gradually it will reach to this final equilibrium. That will be the case. Okay. Now let me run the circuit. So again at time t equals to 0.1 second, the fault will be there. So that's why at time t equals to 1 second, you will see the time. Now again the fault will be cleared at 0.26 seconds. At 0.26 seconds, the fault will be cleared out. And now we are in the after fault curve, and here the circuit breakers will be reclosed.
User can be calculated.
Okay, so normally in the so it is coming here, then it will reach to this point, but in the next cycle it will not go to that F point. Look, it is coming up to this, right? And again it is moving back. Then in the next cycle it is coming here, right? Then again it is moving forward. If we continue this simulation, maybe for more than 5 or 10 seconds, then we will see that the final equilibrium point is here. Okay, that is our delta, previous operating point. Now the question is, what about this time, the reclosing time? This time, actually this time is in practical field. This is in very few milliseconds or microseconds. This is very fast. This time or this angle will be given. Exactly. This is in between the after fault and the reclosing. Because whenever the fault is clear, so again we should connect the line there, right? Yeah, it is actually done by, because there is the relay system. Okay, so relay is the main brain of the protective scheme. Okay, so it will command all the circuit breakers or fuses. So it will command the circuit breaker that cannot reclose. Then the circuit breaker will be reclosed. So now the new topic is the factors affecting the transient stability. I will not go through this class. So there is 2 more pages, right, for this slide. So I will cover these 2 pages in tomorrow's class session. Then there will be another slide, the 2 machine system. That slide is very small. We can also cover that one in tomorrow's class. So in tomorrow's class, actually, we will cover these 2 pages as well as the new slide.